Hello everyone, my name is Jairo Viola and today I'm going to present the work Parallel Self-Optimizing Control Framework for Digital Twin Enabled Smart Control Engineering, developed by myself and under supervision of Dr. Jianshuan Chen on the University of California, Merced. The contents for today, we will have an introduction regarding about what is self-optimizing control, parallel intelligence, digital twin, and how we can combine them to generate a more smart framework. Then we are going to describe the parallel self-optimizing control framework using the digital twin as well as the SPSA optimization algorithm in its basic and parallel versions. Then, based on this framework, a case study will be analyzed to perform parallel self-optimizing control for a thermal system and some conclusions and future works. Okay, to begin, the self-optimizing control is a control strategy that is designed to improve the performance of the closed-loop operation of a system based on an economic cost function. In the classic self-optimizing control, basically it's looking for how to optimize the control variable set points in order to improve that performance. However, that standard definition of self-optimizing control can be extended, as we can see here on the as we can see here. This is the traditional one proposed by Stochastic. We have the perturb and observe. We have including techniques like self-optimizing control, like extremum seeking, economic MPC, maximum power tracking, real-time optimization, zero order, derivative-free optimization in real time, reinforced learning, or batch like run-to-run or iterative learning control. According to the horizon of optimization, the self-optimizing control time scale could be in minutes, days, or months. In the same way, it means that according to the scale, the convergence of the algorithm could be longer depending on the technique that you are using and the dynamic of the system. So in that sense, if we want to introduce some smartness into the system and combine with this self-optimizing control that indeed requires some modeling of the system, digital twin gives a unique opportunity, considering that the digital twin is a virtual representation of a system. In theory, any system can be virtually represented with a high detail with a high modeling detail, performing a lot of further analysis like life cycle or closed loop performance analysis, and also interconnecting with IoT and edge computing, and is supported at the same time by breaking technologies like artificial intelligence or machine learning. So in order to design the digital twin, we can use a framework, in this case for control applications. As we can see here, this framework is composed by 5 steps: target system definition, system documentation, multi-domain simulation, digital twin assembly and behavioral matching, and digital twin validation and deployment. In that sense, following that framework, we can design a digital twin that can be used for control applications, and in that sense fulfill and introduce some smart system properties like cognizant, taskable, reflective, ethical, and knowledge rich in order to enhance the smartness of the system. So based on the self-optimizing control strategy plus the digital twin as an enabling technology, let's think about how we can combine this with the parallel control paradigm. In this case, the parallel control is based on the ACP approach, artificial systems, computational experiments, and parallel execution. This framework is initially used to model social cyber physical systems based on some artificial intelligence models, considering that each subject or individual on the society represents one real-time execution agent of those policies. So what happens if we change or replace these individuals by digital twins that replicate the behavior of a complex process? And each digital twin is able to run on different microprocessors. So in that sense, we can use different instances of digital twin and combine through the self-optimizing control in order to enhance that closed loop behavior of the system. That will be like the big picture. So the main goal of this work is present a parallel self-optimizing control framework that combines those technologies, the digital twin for modeling, the parallel intelligence to support a smart system implementation on multiple instances, and the self-optimizing control through some optimization algorithm that allows the parallel execution, that in this case will be the simultaneous perturbation stochastic approximation algorithm, and in that sense evaluate the virtual world representation interacting directly with the real world or physical asset. In this case, this framework is going to be tested using a Peltier thermoelectric system in order to analyze the viability of this proposal, and two tests will be performed, in this case with and without the incorporation of parallel intelligence. It means using multiple digital twins and just in a regular configuration. Alright, so let's talk about what is the parallel self-optimizing control framework. In this case, the proposed framework for this problem is shown in this figure. As you can see, we have two domains. We have the virtual domain and we have the real domain. In the real domain, we have the physical system or the asset. In this case, the asset is in a stable closed loop configuration. This is something really important. The system is subject to some disturbances, as well as some control laws, sensor noise, and the plan itself. In this case, the controller will be the element that we are going to change using the real-time self-optimizing controller. This controller has some data parameters, which are the tunable parameters of the controller. Those elements are interacting, as well as the reference error and output signals and control action interact directly with this self-optimizing controller, in this case the one using the SPSA real-time optimization, using the parallel execution. Based on the CPA, we have the CPA program paradigm. We have the virtual domain also. On the virtual domain, we have a parallel digital twin that is executing at the same time with the real domain, with the physical asset, in order to compare and manage the system performance and evaluate these self-optimizing control possibilities. So in that sense, we can test the self-optimizing control algorithm, in this case using the real domain and also the virtual domain. In addition, we can enhance the performance of this configuration here using parallel slaves digital twin pool. This pool basically is a set of instances of that digital twin that is the virtual representation of the system. We can use n digital twins as we need or our hardware allows us, and we can use that twins in order to leverage the execution of the parallel SPSA optimization. As well, considering that this is a self-optimizing control strategy, it follows this cost function. Basically, this cost function is in terms of the closed loop performance specifications of the system. We have the overshoot, the setting time, and the error of the system, the quadratic error of the system. We have some weights in this case for each error. So the main idea of this parallel self-optimizing control strategy is optimize the performance of this real domain asset based on this parallel optimization algorithm that is executing in real time with this pool and this parallel digital twin that we have here. So let's talk about the simultaneous perturbation stochastic approximation algorithm. In this case, the SPSA basically is an optimization algorithm that search or looks for minimize a cost function f in function of x variable using a classic stochastic gradient approximation, as you can see here. The main important thing here is that the approximation of the gradient is a recursive approximation and is performed using some stochastic behavior, as we are going to see here. This is the approximation for the gradient descent. As you can see here, this is the recursive approximation, like the finite difference. But in this case, we have here k, we have delta k. This delta k is basically a simultaneous perturbation vector, which is generated in this case by a Bernoulli distribution that is going to change at each optimization step. In this case, the probability of occurrence of this small change ck. That's the main idea of this delta k. And this is going to repeat for all the steps that we are going to execute. We have here this expression that is representing the learning rate of the gradient descent, a over k plus 1 plus a alpha. This is the standard learning rate defined by the algorithm. This is the step size, ck, that we are going to use. As you can see here, this learning rate and step size reduce its size, its step at per each iteration. So that element is going to be reduced as we are reaching the optimization goal. So in that sense, we have the basic and parallel SPSA optimization algorithms. The algorithm can be executed in the regular form. Basically, we initialize the algorithm, generate the solutions, generate the simultaneous perturbation vector, in this case just one for each iteration, or each process. We have just one process. We calculate the gradient using this expression here, and we calculate the next step, and we keep updating this for a certain number of approximations, changing each time our perturbation vector. The main difference, or the algorithm that we want to focus more in this contribution, is the parallel SPSA. This parallel SPSA follow exactly the same steps. The only difference is that we have multiple instances of the parallel system that in this case are going to be replaced by the digital twin. Each instance will have its own perturbation vector, and based on its own perturbation vector, we are going to calculate the next step of the optimization based on this expression here, that is basically the consensus of the regarding to the minimum change on the gradient direction on the optimization process following this norm. So based on this norm, we take the elements for all the parallel digital twins that we are executing, and we choose the minimum one based on this norm in order to calculate the next step. In that sense, we can evaluate more possibilities of this perturbation vector in a more straightforward way. So based on this explanation about the framework, let's talk about the case study. In this case, the case study corresponds to a thermal system, as you can see here. This thermal system has this closed loops execution. We have the thermoelectric element that is going to be a heating element, sensor, actuators, and the control part, working in hardware in the loop execution. For this system, this is the digital twin built in MATLAB, Simulink, and Syncscape, representing all these individual elements with a certain amount of detail in order to replicate the behavior of the real system. That's the main idea in this case of the digital twin, following the framework that we show on the previous slides. In this way, for that system, we are going to execute the framework that we see on the previous one, on the previous section. This framework we are going to use as controller, a proportional integral controller. The controller can be changed to any other. In this case, we are going to keep into a PI controller. The SPSA is going to be tested with and without the digital twin pool. It means the basic SPSA and the parallel SPSA using 5 different instances for a total of 200 iterations, and with these parameters for the SPSA configuration. The initial condition for start the testing is given by this KPKI that will be the output of our optimization algorithm. We want to optimize those 2 values. In order to find this initial condition, basically we identify a first order plus the time model for the digital twin, and based on this first order plus the time model, we calculate this proportional integral gain based on the Sigor-Nichols optimization rules, and based on that, the self-optimizing controller should be able to improve the performance. As you can see here, the obtained results show that in this case, for example, this is the KPKI evolution, this is the cost function. We see that when we use the digital twin, the self-optimizing controller with pool, we have a really good optimization in terms of the execution time. We have 60 iterations to reach the steady state, while with the basic SPSA without the pool, we need 180 iterations to reach the desired performance. So as we can see also here, the response of both systems is really good, as you can see here and also here. Even with this disturbance behavior, we see that the response is really good, and is similar for both optimization cases. The main advantage of this controller is given by the number of iterations. If we use the parallel configuration, we can reduce substantially the time that we can use to optimize the system, especially with this system that is pretty low. Each iteration that you see here takes around 300 seconds to be executed. So this is a substantial reduction on the execution time. So this work introduced by the very first time this parallel self-optimizing control architecture using the SPSA algorithm, and tested on the real case, on this case study of the thermoelectric system. The obtained results show that the SOC framework with the parallel configuration reduce the convergence times of the algorithm and allows to find an optimal response, in this case based on the performance of the system. The parallel self-optimizing framework in this case can be considered as the initial step to introduce more smartness into the loops, support in this case by the parallel intelligence and the digital twin. So in that sense, the next step is the implementation and validation on a real prototype using hardware in the loop experimentation, and also in problems with more variables like hundreds or 10 or hundreds of control variables and control parameters. It's also proposed. Also, another future work will be develop a constraining architecture in order to make the system satisfy some optimal desired conditions. Some references. Thank you so much for your attention. If you have any questions, please go ahead. We will be great to answer all the questions you have. Thank you.